Okay, our next speaker is Ozan Öktem from KTH, and Ozan will speak about task-based reconstruction using deep learning.
Thank you, thank you. We got the tech resolved in 3 minutes. That was amazing. So thank you, Carola, for the invitation and the possibility to present here. It's a joint work with Jonas, Adler, Carola, and Sebastian Lutz. So, and the topic is task-based reconstruction. And what is then task-based reconstruction? Well, essentially it says that, well, what is reconstruction? Roughly, we need to recover some kind of model parameters, which in imaging is the entire image from data, right? And we want to match some kind of observed data here. Now, often we solve inverse problems, and also in imaging, with a certain task in mind. There's a reason why we do the imaging. And typically, the reconstruction part is just one little piece in that entire pipeline. So the typical goal is that you somehow do your reconstruction, and then these model parameters or the image is somehow summarized or maybe post-processed, either by software or a human being, and that these summaries are then used as input to the decision making, the actual decision making. So of course it's natural to ask yourself, can we combine these two steps? Can we do them jointly? And that's roughly what task-based reconstruction is all about. So here is an extract from a radiology journal called Radiomics. The idea there, of course, is to somehow take your images and somehow, using a bit of a loose, rough words, cross-correlate that in some way with your other type of data, and has that as input into clinical decision making. Now the title in this paper are "Images are more than pictures, they are data." Well, I would say they are not data, they are actually usually computed, like up here. So we're actually going to go to the data side. So we're going to take this title here and actually do it properly in that sense. Because as you see here, you start out from a reconstructed image, and then there's a whole pipeline which can be quite complex. But nevertheless, you are starting out from something that's been computed already. It's not data. So how does a regular pipeline look like then? Well, you typically have, it looks roughly like this, the typical workflow in imaging at least. You have one part where you acquire your data, you do your measurements, right? And then you somehow pre-process that data. You always do that. I heard from a colleague that worked at GE that roughly 12 to 16 pre-processing steps are needed before CT raw data is sent into reconstruction engine. Gives you an idea of what's going on here. You have this little box that where most mathematicians tend to be comfortable in. You get this data, you leave out the reconstruction. And then there is typically this feature extraction part that is going on. It could be done, you could do something more simplistic. You could do something more advanced. And at the end of the day, these features are then used for some kind. You can look at them, of course, but you also need to do them for decision making. The problem in doing these, right now, these are often done, I mean, not always, but quite often they are done a bit in sequence. To measure, for example, when you do them in sequence, the processes for each of these boxes don't necessarily communicate with each other. The reconstruction doesn't necessarily consider the task. This task doesn't necessarily consider where the reconstruction, so to say, where the data really came from. Task is often usually done at the very end, and so on and so on. So it's not, I mean, it's not so surprising that the end pipeline is not necessarily optimized for the specific task at hand. So of course there has been development in the field of inverse problems to try to come to do some of these jointly. The most examples are typically going from clean data to extracted simple features. You might push the boundaries a bit, you might go to a bit slightly more advanced features, not only the simplistic ones. Of course, you could be even more ambitious and try to take this all the way to decision making. And of course, you're going to be even more cocky about it. You want to include the pre-processing of the data. And finally, how to acquire it. In some sense, compressed sensing could be an example of part of this red thing, where you say that the features are those that are compressible with a certain dictionary. Well, give me a sampling theory that tells me how to acquire my data. That's an example where you try to go all the way back to how you acquire data. But nevertheless, sparsity is perhaps one aspect of it, but it's not so easy to directly make decision making on sparsity alone in that sense. But but there are ideas. So our ambition roughly will be in this triangular setup. We're going to try to show some examples of doing reconstruction with a bit more advanced than denoising or more, let's say, I'm not saying it's simple to do denoising, but conceptually it's still a simplistic task, so to say. Well, starting out from the functional analytic formulation of an inverse problem, just to set the notation a bit, we have some x2, which is some image or signal or model parameter that we want to recover. We have some noisy data, and we have some forward operator that describes our image formation. So this is information that we have. We might know the probability distribution of this random variable E if we have some good knowledge about the image statistics or data statistics of the acquisition. But nevertheless, the feature reconstruction then is a mid formulation, so to say. We'll tell you, okay, we're not really interested in this image actually. We might have to recover it just because we have to, but our primary interest is some feature that we can extract out of it. Well, from a functional analytic point of view, we'd say, okay, then let's represent this extraction by an operator. You have some set Z, which is your feature set, and you're done. I mean, the inversion is to simplify this dotted mapping here from data to feature. And of course, the pure mathematical point of view would be saying that, well, this is nothing new here really. Why don't you consider this combined operator as your new forward operator? You're done. Well, what's new here? Of course, the whole argumentation here is that this feature extraction operator is highly non-injective. So it really doesn't make sense to even try to consider T composed with F inverse as a new forward operator, so to say. Don't even try to go that route, I would claim. Some examples of, so far, let's say feature-based feature reconstruction are, edges are of course known to be important image features for their interpretation. So we have examples of lambda tomography where you use typically the microlocal properties of how edges are transformed. This is a mathematical description that tells you beforehand how an edge will be transformed under certain operators. You could use that information and actually design a filter by projection type of reconstruction method that recovers the edges. And that's typically called lambda tomography. Of course, we've seen various examples over the days here with TV type of regularizers that in one way or another capture edges but also maybe other features. But edges predominantly are also important here. You could also, we've seen yesterday with the presentation by Gita, she introduced sharelets to you guys, for those of you who were at that presentation. Then you are reconstructing dictionaries that allow you to sparsely represent edge information. So that would be also, again, edge focusing reconstruction scheme. And, oh, of course I don't have, it's not copy beam. You could do joint reconstruction and segmentation. That's another example. I think Christoph was talking a bit about that yesterday, if I'm not entirely wrong. You could, of course, do it also without a variational scheme with approximate inverse. That was after Lewis demonstrated that for segmentation operators that you can actually represent, like an edge candy detector. And you could use the Manfouchard approaches and so on, level set approaches. You could do joint reconstruction and classification. And you can do reconstruction and image registration, either by using optical flow or diffeomorphic deformations or optimal transport. And the references listed here are really incomplete in the sense that it's just an example. So this is essentially the functional analytic framework for doing joint reconstruction and some task-related post-processing in jointly. Now, I would say the drawbacks with these approaches are a couple. First of all, the state-of-the-art approaches are all, I would say all of them are based on variational formulations, because that's where you have the flexibility to encode the feature extraction into the reconstruction scheme. And even though they are sophisticated, they can only handle, I would claim, fairly, I mean, they don't handle the full range of features that you would like to have to be able to recover, so to say, for decision making. And often also, for real decision making, we would like to have the uncertainty of the certain feature. Not only that, it's to get us segmentation is perhaps not good enough. You want to see how likely it is, in some sense, if you're at least going to do some kind of decision making on top of it. So, with these drawbacks in mind, if you want to formulate a bit of a more general program for feature-based reconstruction, you're a bit forced to consider the statistical viewpoint. And here, you don't anymore reconstruct actually an element in the reconstruction space. Instead, you're trying to recover a probability distribution that lives. So X is still think of X as your 3D or 2D images, some suitable set of 2D or 3D images, typically a function space if you're function analytic in the mindset. And you have a family of probability measures on that set, and there is some true probability distribution. That's the one you want to get, right? And your forward model, or your forward operator, is now replaced by a mapping that takes a probability distribution on the reconstruction space and maps it to a probability distribution on the data space. It's a very general formulation. And what you know is that you are given a data set, that is a single measurement. That's not this y is not a random variable, but it's a sample of a random variable whose probability distribution is given as the data model acting on the unknown probability distribution in a construction space. So this would be the statistical formulation of inverse problems. To begin with, there's no feature reconstruction here yet. It's just, or task-based reconstruction. It's just a pure inverse problem. And of course, yeah, I keep forgetting that. Yeah, this is just some notational thing. The idea, of course, is that elements in Py are each probability distribution up here could be a candidate for generating your observed data. That's the whole idea. And typically, of course, you would say, where did my x2 go away? It's gone now. It's not here in the formulation. Well, you could consider a special case where this unknown probability distribution in the reconstruction space is parameterized by some element, right? So if you know this element, this the true image, I'm also given automatically somehow the probability distribution from it, right? Then of course you could somehow recast the problem back to recovering x true. Also in many applications, you really are, especially in imaging and especially in 3D imaging, you won't really be able to represent a probability distribution over volumetric images. That's really data-wise too big of a task. So you are perhaps best in exploring it in various ways, typically done by doing estimators of this x true. This is assuming, of course, that this unknown probability distribution is fully given by this unknown element. But this also opens up for doing uncertainty quantification. That has been also something of interest in the field. And if we really want to relate this back to the functional analytic framework, then of course we can look at the case where this mysterious M, which is actually mapping from probability measures to probability measures, it has a certain form. So it essentially gives you the probability distribution induced by this random variable. And here is your forward operator popping up, acting on the true image, and then there is an additive random variable which has a certain probability distribution, right? This will bring you back to the functional analytic formulation. And you might, of course, include Poisson random measures if you have, for example, in PET imaging, the second line here is actually of relevance. And of course, the task-based version of this framework would then, of course, be that you introduce the set Z again. Now keep in mind here that Z is a set, right? So it can be itself an ensemble of probability measures. It doesn't have to be elements in a certain feature space. But sometimes we want it to be also elements in a feature space, so I keep it a bit unspecified, just calling it a set. And then I have this, I call it task model. I don't know really lack of a better terminology. It takes now, what does it do? It takes a probability measure on the set of reconstructions and gives you an element in Z. So this is the probabilistic generalization of the functional analytic version. And a really special case is, again, if eta true is given by some, this is the probability distribution, and this is really the element, an image. So if eta true is really given by an image, a true image, so to say, then of course you can consider a special case where this mapping A actually is a function operator acting directly on elements in the reconstructions. So this was a fairly abstract framing of task-based reconstruction. Just let's see how it boils down to concrete cases. So let's say we want to do reconstruction and segmentation, right? So X is some suitable space of functions, maybe L2 over a certain fixed domain. Now Y is also a set of real valued functions, but here it's not obvious where it's defined. I mean, it depends on your inverse problem where it's defined, right? So in tomography, typically Y is real valued functions on a certain manifold. And this manifold is given by the acquisition geometry, because here you have lines and you have functions on lines. Or if it's an MRI, then you're suddenly doing in the Fourier space, I guess. Z is now a family of probability measures or distributions over the set of binary images. So I'm giving a binary image, and I'm hoping to get, for each point, or each, let's say, pixel, if I'm going to discretize this whole thing, I want to get a probabilistic value between 0 and 1, telling me how likely it is that this pixel belongs to the object that is segmented or not. So of course you can see that this F mapping, which is call it somehow the task operator, I call it. This guy is essentially a grayscale image, where the grayscale value is the probability of this pixel or this point belonging to the object. Okay? Likewise, you could do image comparison in the same way. Then you have a pair of images that you want to compare to find a discrepancy between them. Likewise, you have a pair of data, right? And they might even come with their own forward operators if you want to have a really nasty setting. And then Z then is simply also images that are, and then this feature operator is, you can even state it non-probabilistically, it's just a difference, right? Or you could do joint reconstruction and classification. You might say, I want to classify what an image is representing. It could be like, rabbits and dogs and so on were mentioned yesterday, or you could do it more easier with the MNIST. You can talk about, for example, which number it represents. But nevertheless, Z is now suddenly a family of probability distributions over the classes, which I just label just labeling them 1 to n. Okay? And of course, you would ask your favorite map estimator for those of you who are doing it, right? So in this case, of course, this operator A takes a probability distribution and gives the most likely candidate, maximizes it. And in a Bayesian setting, this essentially boils down to the map estimator. So you can see that this is a fairly flexible way of formulating in a coherent framework a quite wide range of task-based or even non-task-based reconstruction problems. So this was the theoretical framing. And you might say, well, okay, that's perhaps okay, but I mean, can you do something with this a bit more computationally? So let's take a look at it from a computational point of view. So we introduce 3 random variables, x, which is essentially representing our reconstructions. It's a random variable now, and it has some unknown distribution, probability distribution, right? We have our data y, which is given by our forward operator, in that if you have one available. So it has a probability distribution which is a transformation of the one that x had, which is still unknown. You don't know the eta true, right? And then you have zeta. It could either be just a simple feature, or it could be mapped into probabilities. If zeta is simply features, then you want to have a probability distribution over these features, and it's distributed by zeta. So it's 2 examples. Now I'm going to introduce the concept of learned reconstruction operator. I'm going to talk about it like in a couple of minutes. But let's see that there is some mapping which takes you from data to reconstructions. And it's parameterized in one way. I call it just phi 1. And then, of course, it's been trained, so we are sniffing at machine learning here a bit. I have some nice training data with pairs, and I can train this thing so I can find the best element. And I'm training this. I chose the expected loss. I have some discrepancy measure of closeness in the X space, and I'm minimizing an expectation value of this kind. And of course, all this is replaced by the empirical expectation in the case where you have finitely many data sets, training data. And typically, I might also say that my task operator is perhaps learned, right? In the same way, it maps a reconstruction into the set Z, and it's parameterized by its parameters theta 2 and its obtained with its own loss function, which is definitely the LZ loss function doesn't really have to do anything to the LX one. Now these are so far not talking to each other, right? They are not joint in any way. So here's the idea then. If we happen to have joint training data, that is, if we happen to have access to this triplet of random variables that I introduced in the beginning, reconstruction, measured data, and let's say tasks or features. Okay? If I happen to have the probability distribution of those joint distribution of this random variable or empirical observations, so I can have an empirical distribution, then of course I have a chance of jointly training it. So first of all, I form the composition operator. I of course just do the reconstruction composed with this F part. It goes from data into Z. But on top of it, I could do the joint learning, because now I have two parameters here, theta 1 and theta 2, right? And I could somehow recalibrate them, if I may say so, or jointly train them on the triplet or training data I have up there. And then now this might be perceived as kind of an ad hoc loss function, right? I'm just taking a combination of these two up there. And perhaps this can be done a bit more better. But the constant C1 and C2 regulate how much these two talk to each other in some sense. I mean, these are not human beings, but we will see that they influence each other in a quite interesting manner. And you can also pre-train these beforehand, but this is not the key aspect here. It's actually important to pre-train in certain circumstances. So I'm just summarizing now. So I have a joint reconstruction operator that takes me directly from my data into whatever Z is. It's parameterized by at least two parameters in this way. These could be quite high dimensional parameters, but nevertheless they're finite dimensional. That's important. And they're trained against this joint loss function, which looks like this. Okay? This is essentially the setup. Now it's clear that this reconstruction guy, it needs to be fairly, computationally feasible, but it also needs to be fairly flexible to be able to be trained together, so to say. So I'm going to argue that this leads us to using the learn, train, iterative reconstruction schemes that was just mentioned in the previous talk. I'm going to go through that quickly. And this F operator, well, this can be more generically taken as we will have it as a machine learning approach for these three examples. We're going to do joint reconstruction segmentation, we're going to do joint reconstruction image comparison, and we're going to do joint reconstruction and classification. Okay, but before doing all that, let me say a couple of words about learned iterative reconstruction. So these are the references for what I'm going to say. There's also software for you guys to play around with if you want that. So forget about task-based reconstruction for a second and just think about reconstruction, and let's think about using machine learning to do reconstruction. Now, we know the forward operator, right? And we somehow want to use that information we want to put that information into the machine learning. So the machine learning task is to give us an operator that takes data to reconstruction. That's what it does. And we say that do that while accounting for this side information. You know that this mapping from data to reconstruction, you know that it has a kind of a pseudo inverse, which is the forward operator, which I know. So the idea is, how do I embed that information into my neural network? Before doing that, though, for a second, let's take a look at the variational methods. Now, they are, of course, considered to be state of the art. If they're nice because they're highly adaptable, yet they have a nice plug-and-play structure. It's a generic formulation, but it's adaptable. You can pick this S, which is essentially your penalization for overfitting. You can take a sparsity, or you can take some other thing. That's essentially capturing your prior knowledge. Forward operator is, of course, depending on the physics of your experiment. The choice of this norm, I've written this as a norm. It doesn't have to be a norm, actually. In the Poisson case, it's a Kullback library type of discrepancy term. So essentially, the choice of the distance, or let's say, in a wake sense, depends on your statistic knowledge about the statistics. And of course, the lambda here should reflect the size of the noise, right? So if you have very noisy data, you put a high lambda there. Because you don't trust your data fully. If you have really nice data, you put a small lambda there because you trust your data more. But roughly, when you select these guys in an appropriate manner, you actually are considered to get really, really state-of-the-art results. And there's also this nice maximum a priori estimator interpretation. Now, of course, in the infinite dimensional setting, this interpretation is a bit more shaky. It's a bit more technical to make it in a proper sense, but I'm waving my hands a bit to say that it's doable also in that setting. This is all nice, of course, but there is some drawbacks that comes with the variational methods. Again, as I said in the previously, that even though you can put fairly sophisticated choice of S, it nevertheless captures, I would say, just a small part of the available prior knowledge. If you look at the radiologist that is analyzing a CT image, or a biologist that's sitting with an electron microscopy image, you know, they'll use a lot of information that will be really tough to capture by an S. And you need to pick this parameter. There is some theory for how to pick it when you have additive Gaussian noise. Some theory is done for Poisson noise, but in reality you have mixtures of these. Theory breaks down a bit. You end up picking an educated guess. Right? That's what's happened. And perhaps the worst case that is limiting these methods, especially in the medical imaging setting, is their large computational burden. They just take time to solve. So, since that machine learning has been so hot during this conference, right? We've heard yesterday some, you know, remarkable examples of it. It's of course a bit itches in the fingers. Maybe we can use ideas from machine learning to address some of these deficiencies that were mentioned with the variational methods. So if it's hard to pick a good S up here, just like Stacy was mentioning, can we learn it? And there are a bunch of ideas for how I can do that. Mentioned some of them here. Sure, you can learn it, but you might address the idea of finding the prior, but you still have to solve this variational problem. So you haven't resolved the issue of computational burden. You might turn the trade and say, well, can I use ideas from unsupervised learning and learn somehow my optimization thing? The LISTA, which is the learned ISTA, is perhaps one of the first examples of doing that. It addresses how to some extent, the computational burden part, but it doesn't address the part of learning or picking up this more complicated prior knowledge. So clearly, you somehow need to learn both the prior and how to reconstruct, as I said. If you want to be addressing both the computational aspect and the flexibility aspect. I'm going really quickly here. How much time? When am I supposed to? About?
You have time till 10:40.
10:40. Okay. I'm going to be speeding up a bit here. Well, you can try to reconstruct the whole thing by learn. That's not going to work so well. You can do learning as a post-processing. That actually works quite well. This paper actually essentially won the challenge, the low-dose CT challenge last year. It's just a pure post-processing a Feldkamp method followed by post-processing. But what we're going to do is what is called learn iterative reconstruction. So we're going to learn how to iterate and in a subtle manner. These are the references that we know about right now that are relevant in this context. But this is a fast-moving field, so there probably going to be new ones added. So to present the idea in a very simplistic manner, you say, okay, let's take a look at this least squares minimum. Don't care about right now that this is overfitting and so on. Leave that aside for a second. Just look at this optimization problem and say, I want to use gradient descent to solve this. So of course you get a scheme, updating scheme of this part. Now the computational feasibility lies in this ... here. You don't quite know how many iterations you need to take, right? And there's a whole range of tricks to make this. You stop somehow when you think you have converged sufficiently well and so on. So what if we say, do we really have to update in this particular manner? I mean, this updating really makes sense only if you're going to go on in the limit, right? So what if we beforehand say, I'm going to say, I can only afford, let's say, 10 iterations. That's what beyond that, my application puts time limits to my usage. I can only afford 10 iterations. Well, then of course it doesn't make sense to do gradient descent. There's no logic behind it really. So we say, okay, why don't we retain the pieces that make up this updating, the previous iterate and this derivative gradient expression for the objective, but we learn how to combine them from training data. So let's give you somehow kind of a learn gradient descent. And then of course we know that there are more sophisticated optimization methods out there, so you can essentially take the same idea and apply that in a more sophisticated context. Here it's illustrated for the learned nonlinear primary dual hybrid gradient scheme. You will again replace these proximal steps with learned steps here. And you can also add memory into the primary and dual updates, and that will essentially bring you to the learned primary dual method. It looks a bit complicated, but essentially it's the primary dual, but the proximal is replaced by learning, but you retain the same components, so you essentially have the same information like the variational methods have. But you're now optimizing the iteratives against a finite number of steps. So that is where you address your computational unfeasibility aspect. And this is the network architecture. Yesterday it was said that we don't like images of networks. So I now started with the iterations, so I hope math guys are happy. And this is to satisfy the computer science people in the crowd. This is roughly how the architecture looks like. You're alternating between the primary and dual updates like that in a fairly nice manner. So let's see how this performs. This is a low dose, there's a Poisson laws here, there's a 2D ray transform. It's pi 12 to the square pixels. Training data is about, I think it's about some 9 patients, taken from 9 patient slices. So we have about 2,000 pairs of 2D high dose CT slice, which is somehow our phantom, and corresponding data. And we are pitching 4 methods. We are pitching, of course, the usual filter back projection. We're using the total variation. We do, this is the guy, the third one is the one that won the low dose CT challenge, think of it that way. And finally, we are using the learned primary dual scheme. Now, always when you show Shep-Logan, you don't have to explain anything, right? It's so simplistic phantom. But this guy is a bit more intricate here. So you can look, of course, everywhere you want in this image, but take a particular look at this region. There's a small feature there, right? There's a small gray spot there, right? And here there's nothing. It's fairly homogeneous. So when I'm going to show you the reconstructions, keep a look at those parts where the arrows are pointing. So I'm doing filter back projection here. You get this white little streak here, which is, of course, an artifact. And you get neighboring features of the same size as this gray spot. My hands are not steady. Trying to point to the gray thing here. But of course, doctors know this in the sense that they can see these streaks anyway, so they can, in their heads, they can filter out them, and they wouldn't try to interpret this as a strange elliptical shaped tumor or something like that. Well, you throw TV on this one, yeah, it dampens down a bit, but it still is marred with the same. I mean, clinically, we haven't really gained so much here. The image looks nicer to look at. Actually, the doctors don't like this one. They like this one more than this one. And this is not only of pure conservatism. It's because here, these more clear feature streaks are aiding them not to interpret this thing as a true feature here. Whereas if you damp them out, we could have thrown TGV on this too. We'll damp them out even better. Then you get the false impression that what's left is true. And this is what they don't like. And then you can do the post-processing with the neural networks. But you see, in all of these, you don't really address the issue of these false structures. And when you do the learn primal dual, this is what you get. They are gone. So you can, of course, look at PSNRs. But at the end of the day, we're talking about clinically useful improvements. And this was an example of clinically useful improvements. And on top of that, take a look at the runtimes. Now, if I would run TGV on this one, I would have an even more brutal runtime here. This is almost in the border. I mean, this is, we are talking clinically useful runtimes. So this is, I would say, quite an interesting thing. Now, yeah, in the interest of time, this is just showing the impact of choosing your loss function properly. I'm skipping this, I'm sorry, and moving on to the task-based. So now let's go back to the task-based one. So the reconstruction method we're going to use is the one that I was explaining to you. And it's not just because it performs well, because it has a flexibility. It allows us to jointly train it with the post-processing neural network. That's actually the main reason. This is just a recap. We have this learned iterative reconstruction scheme, which goes from Y to X, as explained before. So the forward operator is in there. Keep that in mind. We capture the physics knowledge. We capture the information about the noise statistics and so on. So there's a lot of things that are captured in this neural network. We do learn task operator. That's going to be more like the off-the-shelf versions. We're combining them. We have two distance notions, one in reconstruction space, one in task space, so to say, or feature space. And we do the joint training by this nasty expectation minimization. So let's do the joint reconstruction and segmentation. The problem is not the one that we had before. It's going to be brain. It's going to be fairly, now we took a smaller image. It's parallel beam ray transforms. Just for all of these examples is a bit, simplistic, but it's just to provide the idea. They're by no means optimized really to the fullest. I mean, you can do this a bit more carefully. So we have training data, 100 triplets actually. This is a 2D image corresponding tomographic data corresponding true segmentation map. Okay? That's what it's training on jointly. Here there is no pre-training, so it's directly training on these triplets. And then this is, we use the L2 distance in the image space as the loss when we are training for the image reconstruction part. We are using the cross entropy because the outcome of the segmentation part is a probability map. Keep that in mind. So we need a notion of distance between probabilities, and cross entropy is one way of doing it. It's the standard unit actually that's being used here off the shelf. And then of course they are jointly trained, right? Keep that in mind. They're jointly trained, and we just took this joint loss function of this form. And these are here is the values, it's a log-log plot of these loss functions. And here are each of the, I'm going to call these channels now, they're not really channels in a multi-channel imaging really, but let's say this is a reconstruction channel and this is a task channel, so to say. We immediately see here that for each choice of C, this seems to be reasonable. Keeping that in mind that for each, for C's, reconstructions are fast. Once they are trained, they are fast, right? You can even have a slider, almost, I would dare to say, to do reconstructions on real data. So here's the phantom, by the way. Down there is your true segmented map. This is ideally we want to recover. In the task sense, we are not interested in the above one. Not interesting. I'm just showing it just for the sake of showing it. This is the guy that we want. Okay? So with a low C value, what does that mean? That means simply that we don't, low C value means that the joint training really de-emphasizes the reconstruction channel. Okay? With a low C value, this is what you get. You get these grayscale values are probabilities, take that in mind. And as we increase it here, only around 10 is actually quite nice. Even this one appears now quite representable. Now take a look at what happens if I go to 100 here, right? So you get the spurious little stuff in there. So I'm going to talk about these guys as if they were human beings, but of course not. But to some extent, these two channels are communicating with each other, because the segmentation, in some sense, tells the reconstruction part, look, there is nothing there, right? So the reconstruction part says, oh, then I'll deposit my high-frequency noise terms in that region. I'm just guessing a bit, but the rough intuition a bit is like that. So it tells you that, and for each choice of C, this is a really fast reconstruction. So you could essentially, if you have pre-trained them, you could go in between these like here. But apparently you can also see that 10 seems to be a reasonable number here. It's fairly low. It's not the minimum, but of course it's perhaps a good compromise. You can see that from the training. So you can actually quite pinpoint a reasonable C rather quickly. So it works actually quite decently, I would say. Let's do the joint, essentially, this is a bit of a simplified, we're using the same forward operator now, so we don't have two different modalities or something like that. So we have the same forward operator, same size, same geometry, it's a bit simplified, but nevertheless, we have pair of images, pair of corresponding tomographic data, and their true difference. Okay, that's what we have. So you are jointly training on training data of that type. Again, the reconstruction part is the learned primal dual one in each channel-wise. So there is no fancy, cross structural thing going on here. not in the reconstruction part at least. And of course the corresponding L2 distances channel-wise, sum of channel-wise L2 distances. The task operator is essentially a U-net that has been trained on mapping on differences. So that's nothing more than that. And then you do the joint training. And here, of course, this term is a bit more complicated. It inevitably depends on both parameters here. What are you doing? You're taking the reconstructed pair. This outputs a pair of reconstructions that is fed into the neural network that is somehow supposed to give you the difference image, and that's then compared against the real image, a real difference in your training data. Okay? And then you're training this thing plus the reconstruction channel itself. Yeah. This is your plots for these losses, how they look like in the log-log plot. But more interestingly, let's take a look at the results. So this is now a simplistic case with a phantom. It's a bit easy to see the difference here. So here, the anomaly is this little square that's been inserted. It's of course not really medical right now. It's just a discrepancy. So this is the true distance. The true difference image. Looks like that. And these are the two incoming phantoms that you don't know about. And here you can play around with different C values. It's actually fairly stable, I would say. Again, around 1 or 10 is a good match, right? But then it's actually fairly insensitive. So even though these guys up here could differ quite a lot, the part that's related to the task is fairly stable with choice of C. But of course, if you also want good reconstructions, you have to be a bit more careful with the C part. Okay? And the final example I'm going to show you is from classification. Now, we took the MNIST images. This is a bit of an odd case, right? You take tomography on these handwritten letters. We are just doing it to show you the idea. Of course, there is no use case for doing tomography on handwritten digits. But gives you a flavor of how things can work. Here is Poisson noise. The images are really small, 28 by 28 pixels. You have triplets now. You have your handwritten digit image. You have the corresponding 5 directional. You have 5 directions. Parallel beam tomography is really undersampled by all means. You have your tomographic data here, and this is the class, the true class that this image is belonging to. Does it represent a 0 or does it represent a 1? What is it? And of course, we want to do the joint. Here we are doing joint training, so we are doing the learn reconstruction method again for the first part. We are doing the task operator now is a classifier. It's again an off-the-shelf classifier. We didn't really put that much effort into it. And the loss measure there is the entropy, and then you do the joint training here. And now we actually did it with C equals 0, if I'm not wrong. So 0. So we actually, when we did the joint training, we didn't at all account for the reconstruction part, in the sense of course, the reconstruction part is in there, but the training is only focusing on the classification part. It was pre-trained, this task operator, and it had an accuracy of about 97.5%. Somebody said yesterday that MNIST is a fairly simple classification example. So we're hardly going to beat this example. If we beat this one, that would be a bit of a sensation, right? But so think of this as the ground, the holy grail to get to when it comes to accuracy. This is training directly on the clean images, the noise-free images, clean ones. Now we're going to do the classification on the noisy tomographic images, and that's a different ballgame. We can do it in 4 different ways. The last one is the most sensible one when you do the joint training, but so just take a look at this one. The first line is that you do them sequentially. They don't talk to each other. You do reconstruction followed by classification. Already that, still you get 93.3%. That's not bad. I mean, at least I don't think so. And then you can do joint training. Actually, here you can see it's interesting also that if you train, if you the reconstruction operator is trained with the cross entropy loss, that gives us a worse. That's a bit odd to do that, and it's also reflected in the accuracy. You can see it drops. But if you do the joint pipeline, where you jointly train them, this is the pre-training part. Sorry, right? Then you get 96.6% accuracy. It's fairly close to the one that was 97 points. What was it? 97.5. But also let's look at some images just to see. It's fun to see how it performs. So these are 4 reconstructions of 4 MNIST digits. Yeah, that's how they look like. Can you see the integers? Yeah, you can't, right? That's the point. Take one of them. So I don't know if you can see. Well, let's actually do the classification and reconstruction in a sequence. Then we get this table. It says it's going to be a 9, and it's confident about it, 99%. If we do the joint reconstruction and classification, this is the table we get. Oh, both are confident. It's even more confident here. This is a 9. Now, being a human, we could be a bit skeptical. We saw the example of the car derailing yesterday or something like that. So we really want to look at the reconstruction, right? Just to double check. Well, if you go in this part, you go up to the filter back bridge. I'm not so sure if you are helped by looking at the reconstruction. Maybe if you are really trained and, you know. But if you look at our reconstruction, that's what you get. It's the reconstructed channel. Now you can say, it's a 9. Sure, it's a 9, of course. And then you look at the ground truth, and it was indeed a 9. It's a bit irritating that this damn thing is doing pretty well over here. It's a bit, I say, quite fascinating. Well, let's go on. Here's another one. I think this one was totally hopeless. The 9 I think I could solve, but this one is totally hopeless, for me at least. Well, let's look at the table. It says it's a 4. Again, it could perhaps be a 7, right? But it's 4. We do the joint reconstruction and classification, and surely enough, it's actually a bit less confident that it's a 4. It says